Hi guys, once again guys we come to solve this problem. And so guys, let me first read the question. It's actually a system modeling question. And I read the question. Given the figure 1, find the differential equations of the system. Roman 2, transfer function x2 and then s all over fs. So guys, this is our system. And so guys, we are going to have to do this by drawing the space diagram for M1 and for M2. So guys, the first thing we are going to do is to draw the space diagram for M1. This is the space diagram, and as you can see guys, here we have, if you look at what is attached to M1, we have a spring, we have the damper. And guys, this moves in this direction, so we shall have a force of inertia on the opposite direction. And so the forces will be like this. We shall have the damper force acting opposite of the force that is applied. And this other force is the force of inertia due to the mass of the system. And so guys, when we now come and write the equilibrium equation, we shall have Fm plus Fd equals to Fk. Guys, now we write it in terms of the differential equations. This is how we write it: m1 dx squared x1 over dt plus this is the damper dx1 over dt is equals to now that. Guys, we rearrange that one so that now we can actually say this is our differential equation. Even these ones are also. But this is where now we come up to that point. Guys, we can change that into Laplace transform now. Converting that to Laplace transform, we are just introducing s and this s. This is Laplace transform. For that is s squared, x is this one, and for the others, just as it is written, make sure you have this s, which represent the Laplace transform. For the damper, you have an s there. For the mass, that is acceleration, you have s squared there. And guys, from there we can factor out x1, because remember guys, our question is asked about x2. You can see we are looking for x2 here. And so guys, we need to factor out x1 so that we shall be able to eliminate it. So this is what we have for x1. Guys, we do that so that we shall be able to eliminate it after getting the other differential equation of M2. So we go now to a space diagram for M2. And as you can see guys, here M2 we have two attachments. We have this attachment of the spring and we have this other force. So as it moves this direction, we have another force here. That is due to mass, due to inertia of that mass. We call it as Fm, acting opposite to the direction of the mass or the direction of movement. And so guys, we have our equilibrium equation right here now for the mass 2. And when you go ahead, you can write now the differential equation for that. So after writing the differential equation, guys, as you can see, I have already moved ft. This ft is this, and these other two are this right here. And as you can see, the k, because we are dealing with the k this side, you can see the k is not fixed, so it will have at this edge it remove x1, and at this edge remove x2, and so the expansion of that spring will be x2 minus x1 as it is written right here. And then therefore guys, that is the second differential equation. Guys, we convert to Laplace transform, and this is what guys now we get as our Laplace transform. Guys, we come now and replace for x1 with whatever we had found here. This is what we are now replacing for x1 because we don't need the x1. So when we replace that, guys, this is what we are now going to have. In replacing for x1, we have this. This is what we are now replacing with x1. After we have replaced that, guys, we now come and factor out the x2. We can factor out the x2. When we factor out the x2, this is what we get, x2s. And then, guys, we can now make the whole of this under the same denominator of that, which means we multiply this and that. And this is what we get, guys. We multiply that and the equation is going to be like this. The last thing, guys, we just move this f to this side and the whole of this to this other side. That is to be able to get our transfer function, and therefore our transfer function is as shown. Guys, thank you for listening to me. Bye.